Hello, everyone, and welcome to Calculus. In this section, we are going to introduce the idea of limits. So let's get started. When you think about a limit, I want you to think about two words, approach and approximate. What's going to happen for us is that we want to approach x, and then we're going to use that approach to approximate y. And that's really what a limit is doing, is it's approaching a specific x value, and then we want to approximate what's going on with y, which makes this really interesting because the function does not even have to be defined at that x value in order to have a limit because we're approximating y. We don't really care what that exact value is. So let's look at some notation. So the notation for the limit is going to look like this. And so you see that arrow here, x, that we read that as x approaches a. So the limit as x approaches a of f of x is equal to L, where L is going to be some finite value. There's going to be some examples where we're going to approach a finite value. There's going to be some examples where we may not be approaching a finite value if we get close to a vertical asymptote. What's going to happen is that everything's going to go up to infinity or down to negative infinity. Or there's going to be some places where that limit just does not exist. And we're going to see examples of all of those. The formal definition for a limit is based on the idea of distances, and they're going to introduce this as epsilon and delta. So the formal definition says for every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. So here's what this definition is really trying to say. Epsilon and delta are distances. This is going to be an x distance, whereas epsilon is going to be a y distance. So let's look at a generic graph. This is going to be my f of x function here. I want to know what's happening at a, and I know that limit. We haven't talked about the graphical approach yet, but we will soon. It's going to be L. So the limit as x approaches a of f of x is equal to L. So what this definition is saying is that we're looking at an interval around that x value. This distance would be delta. So if I look at that interval, it's going to create an interval around my actual limit. You can see how I can go up to my graph and then go over to the y-axis. So this distance is epsilon. And as I make that interval smaller and smaller, so I make that delta value smaller and smaller, we're squeezing in on that x value. And what's going to happen is we're going to squeeze in or zoom in along that y value also. So you can see how that blue interval is much smaller than that red interval. And that's because my delta value here is smaller than what that red one was. And that's really all the limit definition is saying. So as I close in along A here, which is an x value, then it's going to close in along the y's here. So how would we find a limit? Well, we're going to start with by using a table approach. This is an analytical approach. So we're going to take the limit as x approaches 3 of x squared minus 4. Now, there's an understood parentheses here, which means we're taking the limit of the function x squared minus 4 as we get close to 3. Now we want to know what's happening to the left of 3 and to the right of 3. So we want values that are really close to 3. So 2.9 is pretty close to 3. But we can get even closer by looking at 2.99 and then 2.999. Likewise on the other side, 3.1 is pretty close, but I can get closer by looking at 3.01, and then I can get even closer by looking at 3.001. And what we're doing is as we zoom in, we're looking for patterns here. What are we getting close to on this side and on this side? And so I'm going to compute these things off screen. I'm plugging each of these in here and I'm figuring out what is the Y value associated with 2.9, 2.99, and so on. And you may want to pause the video and plug all of those in and then come back and check your answers and then we can talk about what that means. So at 2.9, I got 4.41 as my Y value. At 2.99, I got 4.9401. 2.999 is 4.994. On the other side, 3.1 gave me a 5.61. 3.01 is 5.0601, and 3.001 is 5.006. So I'm asking, what are these Y values getting close to? And I want them to get close to the same thing on the left and on the right. Later, we're going to talk about left and right limits, but right now we're looking at the limit at 3. And the left and the right-hand sides have to go to the same place for this limit to exist. And as I get close on the left, these values are getting close to 5, and then the same thing on the right. So we would say that limit is approaching 5. Now let's graph this in Desmos. Desmos, we're looking at the function y equals, y equals x squared minus 4. I want to know what happens as I get close to 3. And from the left, what that means is we are going to follow this graph to get close to that y value of 3. Sorry, the x value of 3. And then we're going to follow that graph on the right-hand side. So I'm zooming in around 3 on the left, and on the right, it's getting close to 5. Now, it just so happens this guy is defined at 3. So now let's look at the next one. We're looking at sine x over x. We want to take the limit as x approaches 0. So we're going to get close to 0 from the left and from the right. From the right, I can look at 0.1, 0.01, 0.001. And on the left, I can look at negative 0.1, negative 0.01, negative 0.001. You want to make sure your calculator is in radian mode. Almost everything we do with trig functions will be in terms of radians. So I'm going to type all these values in off screen. So I got 0.9983, 0.9999. Now this would really round to 1, but I want to show there's a little bit of a difference there. So you can see as we come in from the left and from the right, this is approaching 1 also. But notice in this case, that function is not defined at 0. But what's going on is that we have a hole. So let's graph this one. Y equals sine x divided by x. Here's our graph. Notice that at 0, the function's undefined, and that's because there's a hole there. Desmos just doesn't do a good job of showing that hole. But as I get close on the left-hand side, I want to zoom in on this area. So I'm going to follow the graph on the left. That y value is getting close to 1. And if I follow that graph on the right, that y value is getting close to 1. So we would say the limit it's going to be 1. Let's look at that next one. We're going to do the same thing here. And this is where you may want to pause the video and try the next two on your own. All right, let's talk about the next two. So if I look at this one, I'm approaching 4. So I'm going to look at values like 3.9, 3.99, and 3.999 on the left, and then 4.1, 4.01, 4.001 on the right. And you can see that as we get close to 4 on the left and on the right, this is getting really close to 0.25. So what's happening here is that we have a hole at 4. And we could see that if we were to do some fancy math here. So we could factor that bottom. That's really a difference of squares. We just don't usually think about it that way. So that's square root of x minus 2, square root of x plus 2. And you can see how those reduce. And that gives us 1 over the square root of x plus 2. This function looks like this as long as x is not equal to 4. Because if we were to plug a 4 in here, then this factor would be 0. And that next one, we're getting close to 1, so we could choose these x values. And when we evaluate, we see those y values are getting close to negative 0.25. Let me fix that. I was looking at the wrong thing and I apologize for that. So I've gone back and I've corrected this. I was looking at my wrong column in my calculator. So when we plug in this function and we look at plugging in these x values, these are my outputs. So you can see as we get close to the left, to 1 on the left and then 1 on the right, these are getting close to the value of negative 1. So we would say that limits negative 1. Now, notice that it would be really easy to make the assumption that 1 would be a vertical asymptote, but that's not going to be true. To find vertical asymptotes, remember you have to reduce functions, and this is a complex fraction, just like that last one. It would be really easy to make the assumption that 4 would be a vertical asymptote, but it's not. So how would we simplify this? Well, we need to get rid of the complex fraction. So let's multiply the top and bottom by that least common denominator in the numerator. And then we can factor a negative out of the top and the bottom factors. And you can see how that x minus 1 term factors. So this guy actually looks like negative 1 over x as long as x is not equal to 1. Because at 1 we have a hole. And that's what this limit's really showing, is that the function is not defined because of the issue in that denominator here and here. It would make it 0 if we plug in those numbers. But even though the function's not defined, we are getting close to a specific y value, which means there has to be a hole there. Let's look at the next two. This is where you may want to pause the video, come back, and then check your answers. So let's talk about the next 3 examples. So if we were to graph that first one, the absolute value x minus 1 over x minus 1 is going to look like this. And you could graph it in Desmos or your calculator. I'm approaching 1 from the left and 1 from the right. So here's my left and here's my right. And you can see the left-hand side is going to get close to negative 1. In fact, all those y values are going to be negative 1. And that right-hand side is going to get close to 1. So the left hand and the right hand sides don't match, which means this limit does not exist. Same thing's going to happen in that second one. We'll have the absolute value of x squared minus 4 over x minus 2. So I'm approaching 2 from the left and from the right. As I come in from the left and I follow that graph, my y values are getting close to negative 4. And then as I come in from the right and follow that graph, my y values are getting close to positive 4. So the lefts and the rights are not the same, so this does not exist. And then that next one, sine of 1 over x as x approaches 0. So I'm coming in from the left and from the right. So it looks like I could be getting close to something here, but look what happens when I look at negative 0.001. I jump from positives to negatives. Same thing over here. I start out with negatives and then I jump to a positive. This is a really interesting graph. It's an oscillating graph, and what that means is that if I were to zoom in on this, you see that it just starts squiggling. As I get closer to zero, this thing just keeps oscillating back and forth, and those oscillations are super close in here versus out here. Let's see if it'll let me zoom in so you can see it kind of breaking apart here. And what's happening is that graph is just jumping up and down so fast that we can't really find out what's happening at zero. So that limit does not exist also. I'm trying to zoom in, but uh, my fingers keep catching the graph. See, even if we zoom in a whole lot, it's the oscillations are just getting so close to each other that it's just not possible to zoom in enough to find out what's going on. So this does not exist. So we're learning some places where the limit doesn't exist. So one of those is if we have a gap, like up here with the absolute value problems, we had a big gap happening. The limit didn't exist there. Another one is if we have an oscillating graph, where as we get close to a particular x value, that graph just starts oscillating back and forth. And then the third place would be where we have a vertical asymptote. So now let's talk about limits in terms of graphs. And we've already touched on this a little bit. Let's say we have this function and we want to find the limit of g of x as x approaches -1. So we're coming in and we're getting really close to -1. As I get close to -1 from the left, those y values are getting close to 3. And as I get close to -1 from the right, the y values are getting close to 3. So we would say 3 is going to be that limit. Now you got to be careful and don't mix it up with finding g of 1. Because g of 1 says find the value of the function at 1. And the value of the function at 1 is actually at the solid dot, which is 4. And notice that these are not the same. So even though the limit exists, this is going to lead us into the idea of continuity, and we would say this is not continuous. And we'll talk about continuity in a few sections. So let's look at this one. We want to find the limit as x approaches 2. So I'm zooming in on this 2. I'm coming in from the left and from the right. And you can see all those y values are getting close to -1. So let's talk about how do we evaluate limits. The limit as x approaches a of x is just going to be the a value. And that has to do with what that function looks like. Here's y equals x. That's the identity function. So if I want to know what's going on here, may it be at 3? You see that y value would be 3. If we're looking at a constant value, maybe like y equals 2, anywhere along that graph, that y value is going to be the same, so it would be whatever the c value is there. And that's going to help us be able to analyze limits using an algebraic approach. But before we do that, let's talk more about left and right hand limits. So if you see this notation with that negative in the exponent, this is taking and looking at the limit on the left. And this would be a right-hand limit because we've got that plus there. And what that means is that's all I care about, looking at that limit from the left or from the right. Let's go back to one of our absolute value examples. Let's say we're looking at the function g of x equals x minus 1 absolute value over x minus 1. So when we graphed this before, it looked like this. So if I want to find the limit as x approaches 1, we said that did not exist. But what if we just care about the left and the right-hand side? Well, if I just care about the left, I just care about what's going on over here. And all those y values are going to be -1. Whereas if I look at that right-hand side, all those y values are approaching +1. Well, what if we have a piecewise function? How would we evaluate limits? Let's say we have this function, f of x equals x plus 1, as long as x is less than 2, and x squared minus 4 if x is greater than or equal to 2. We want to find the limit on the left, so we're going to end up using this piece. And we can find that limit algebraically really by just plugging in what our values would be. So if I look at this one, I'm going to use the first piece, and I'm going to plug in 2, because this is what the graph would look like to the left of 2. And that's going to give me a limit of 3. If I want to look at the right of 2, I'm going to use that second piece, which is down here. So I'm going to have 2 squared minus 4, which is going to be 0. So this limit on the left approaches 3, on the right approaches 0. Let's dive a little bit more into this algebraic approach. So I'm going to go back to some of my previous examples, and we're going to talk about these a little bit more in detail. So let's review this one. We said that we could factor the bottom and simplify. So then the limit as x approaches 4 of this would be the same as this. So let's plug in that 4. So that's going to be 1 over 2 plus 2, which is 1/4. And you see that's what we got when we simplified, when we looked at that graph. We could do the same thing here. This limit is equivalent to finding the limit of -1 over x. And if we plug in that -1, oh, excuse me. If we plug in that +1, we're going to get that limit to be -1. So if we want to solve these algebraically, all we have to do is plug in the value. Same thing here. If I want to find that limit algebraically, I'm going to plug in and get that y value. This one would give us an issue because we need to find sine of 0 over 0. And 0 over 0 is undefined, so we would have to use the table approach for this one. Or we could graph it. Either one way would be fine. So this theorem is saying the only way the limit exists is if the left and the right hand limits match up. And we've been talking about that already. But let's look at a few examples of finding limits by algebraically. Say we want to find the limit as x approaches 3 of 2x plus 1 over x minus 4. So we could use the table approach, or we could use the algebraic approach. And the algebraic approach just says all you have to do is plug in your numbers in for x and then simplify. So that would be -7. Let's look at the limit as x approaches 4 of x squared minus 16 over x minus 4. So here's a problem. If we plug 4 in, we're going to get 0 over 0, and that's undefined. Anytime you get this, that's a key to let you know you need to simplify this somehow. Now, we know that this is going to factor and reduce. So now I'm really just finding the limit as x approaches 4 of x plus 4, and that's going to be 8. So what's happening here is that at 4, we have a hole in the graph. So now we're going to get into this idea of infinite limits. Infinite limits are going to happen when we have vertical asymptotes. And we can look at this limit from the left or from the right. So technically, these limits do not exist. However, they do not exist in a particular direction. So what we can do is notate the direction there. So let's look at a few examples. Let's say we want to look at 1 over x. We're going to find the limit as we approach 0 from the left, from the right, and then at 0. So 1 over x we know has a vertical asymptote at 0. And that graph, the reciprocal function, looks like this. So as I get close to 0 from the left, I'm following this piece of the graph, and you can see it's heading to negative infinity. On the right-hand side, we're heading up to positive infinity. So I could talk about the direction. Technically, these don't exist, but they don't exist in a particular direction, and we're just notating the direction in which the limit doesn't exist. Okay, at 0, though, one side's going down, one side's going up, which means that this limit does not exist because the left and the right are heading to different places. And that's going to be different if I look at 1 over x squared. 1 over x squared looks like this. So as I approach 0 from the left, this is heading up to positive infinity. From the right, we're heading up to positive infinity, which means that from both sides, we're heading up to positive infinity. And it turns out that's actually the definition of a vertical asymptote, is that unbounded behavior. And that's what we're looking for. And the definition of vertical asymptote says, as you get close to some particular value, if you head up to infinity on one side and negative infinity on the other side, or if you're heading up to infinity on both sides, or down on both sides, then you have a vertical asymptote. So it's just some kind of unbounded behavior somewhere. Let's look at a few examples. We have 1 over x minus 2 to the third, and you could graph this in Desmos. It's a transformation of 1 over x cubed. has a vertical asymptote at 2. And this graph looks like this. So if I look at what's happening from the left, this guy is heading to negative infinity. If I look at what's happening from the right, it's heading to positive infinity. This guy would not exist because they're unbounded in different behaviors. But what we know is that we have a vertical asymptote at x equals 2 because of that unbounded behavior. So let's look at this one. We've got this graph and we're trying to find just a whole bunch of different limits. So as x approaches negative 4 from the left, that y value is going to be 0. As x approaches negative 4 from the right, that y value is 0. So as x approaches negative 4, it's going to be 0. And f of negative 4 is going to be 0. Negative 2, we have a hole. From the left, that limit would be 3. From the right, that limit would be 3. So the limit at negative 2 would be 3, but there's a hole at negative 2, so that function is actually not defined there at negative 2. At 1, that left-hand limit is 6 on the left. On the right, it's actually at 3. So the limit doesn't exist at 1, but f of 1 is defined by that solid dot, and that is 6. And then let's look at what's happening at 3. On the left-hand side, we're heading to negative infinity. On the right-hand side, we're heading to negative infinity. So if I look at the limit at 3, it's unbounded on both sides in the same direction, and that's negative infinity. But the function does not exist there because we have a vertical asymptote at 3.